Dear colleagues, so I'm happy that the volume of people I see not changed from the previous lecture, maybe a bit expand. I'm happy to present the last lecture of Lara Faoro from the Google Quantum. Let's start.
Okay. So in this lecture, we will talk on the coherence, and as you see, we know that the qubit unfortunately interact with many other degrees of freedom, and we can separate somehow in two columns all these degrees of freedom. So there can be spurious dissipative electromagnetic modes, there can be moving vortices in superconducting films, and then we have quasi-particles. And then we have other degrees of freedom that are more due to the electric noise and to the fact that, as we discussed last lecture and with Jürgen's presentation, there are two systems. In particular, what I want to focus, and as you will see, there will be a very unpleasant features of these TLS, that is the fact that they are not only there, but they are unpredictable. And the fact that they are unpredictable is due to the fact that there are moving free electrons that go and change their electric field around. And also the fact that we have high energy phonons. And then, of course, there are also random magnetic spins at the interface. There are two-level system in the junction. But what I want you will see in this lecture, that unfortunately, there is a huge interaction also between the quasi-particle with all of this. And all of this sort of noise that we should discuss today, they involve, in some degrees, material science study, because what you will see is that in order to solve this problem, we need really to have an help from physical chemistry, because the fabrication process is crucial. And so, in other words, the suppression of all these defects is not only, it's just partially a physical problem. So, it was told that the problems come from the surface interface. But you will understand that it's not only the surface and interface that are crucial. A lot of guilt is due to the substrate too. So we know we are doing with transmons or resonators, they have this planar geometry. And we have different interfaces that usually are highlighted. There is the substrate air interface, there is the metal air interface, there is the substrate metal interface. And what is crucial is that we know that these are electric materials. There are different TLS here, but of course the TLS, in order to dephase our qubit, interacts with the electric field. So what is crucial is, first of all, to know what is, where the majority of the electric field is hidden. And for this, one needs to study what is the participation ratio. And then what you see is that depending on the thickness of this interface, you clearly see that the participation ratio is different from, for example, if you consider the metal layer has, for the little thickness, the least participation ratio. The substrate here is like this. And what we have, the majority of the participation ratio, is this interface, that is the substrate metal interface. Another thing that we need to take care and understand is that the process that happen at the metal interface are very different from the substrate metal. Because on the substrate metal, the material are restricted by the constraint that you have to suppress the free electrons that come from the substrate. And also there is a big problem. For example, if you work with silicon, and we prefer silicon for many reasons that we highlight in the following, silicon is a chemically reactive. so it's unfortunately, he wants to form silicon oxide, so it's quite bad. But the metal interface has another problem, that it is not only affected by the air, but it's affected also by all the contaminants. So in order to characterize this, we need to keep into account the fact that they are affected differently. So, but what is crucial is the fact that we have some metal oxidation. So we have the superconductor, and then it oxides. So, first of all, let us see what is known about the theory of metal oxidation. Indeed, there is the theory of metal oxidation was done a very long time ago, in 1948, and actually this model, this Cabrera-Mott model, is still what is confirmed even in recent experiment it holds. So what is the idea? The idea is that you have a metal, and the metal goes into contact with molecular oxygen. And what happens is that there is a migration, there is absorption of oxygen, meaning that you have some electrons that attach to this oxygen. So at the beginning you have this sort of reaction. So the molecular oxygen gets some charge, a negative charge from the metal, and then it creates these absorbents that are with some negative charge. Usually it is, this Z is 1 and 2, and what we denote with Q will be an electron charge. So then what happens? What happens is that you have an equilibrium of the chemical potential, electrochemical potential. So basically you have the chemical potential of the oxygen molecule, the electrochemical potential of these electrons that you have, and then of the new adsorbent that you form. And then as a result of this equilibrium, what happens is that there is, of course, a voltage here, a potential, electric potential here at the metal and oxide and the oxide gas. And basically, when you try to equilibrate, what happens is that you see that you form a potential, an electric potential. And this electric potential that is here has the feature that is so you have migration of electrons here that becomes charged, and there is a formation of this electric potential, and as a result of this, the positive positive carton from the metal starts to get out. And of course, what happens is that when you have a very thin insulator, the electric field is very high. But as your oxygen oxide start to grow, this electric field start to become weaker. And then this migration of this positive cation stops, and then as a result, your films stop to absorb the oxygen. So indeed, what you see in this model is that you will have a very quick exponential growth, and then you have that your system doesn't grow anymore. What is crucial in this theory is how this migration happens. Basically, this migration happens because, as I told you, you have these oxygen negatively charged absorbed molecule that comes close by, and then from this metal, this cation gets out, and when they get out, basically they create vacancy. And so this is how the oxygen, the oxide grows. And it grows, leaving this vacancy. And then I will show that these vacancies actually are really crucial for the formation of this two-level system. Now, this is a general theory for the metal oxidation. But there was very recently a study in which they were trying to analyze more deeply how aluminium oxidation happens. So, again, what happens is that you have your aluminium, and then you have your oxygen, and then the way in which you form the oxide is through this chemical reaction. And then what you see is that depending on the coverage of this oxygen that you have, you see that the aluminium oxide, for example, grows up to 22 Armstrong, and then the absorption of this molecular stops. And indeed, this is a very nice feature of this aluminium oxide that we use in the fabrication of junction, because somehow this aluminum oxide stop its growth around 1-2 nanometer. That is really what we need in order to fabricate a junction. That's why we love aluminum also a lot for this stuff, and that's why one of the features why we have junction only with aluminum oxide. Now, as I told you, we have this absorption of molecular oxygen, and close to the metal, then we have the migration of these molecules that have 2 or 1 negative charge. And then there was an analysis on that, in which they tried to dig what is the kind of species of these molecules that we have. And then you see something very interesting, that in the first layer we have O2 minus, just in the first layer, and this doesn't carry any spin. But in the other layers that are really very close to the aluminium, in aluminium we have O2 minus, and these unfortunately are carrying spin 1/2. And then you start to see that we start to be very worried, because you have formation of spins 1/2 that is very closer to the superconductor. And so you can imagine that there can be interaction with this spin with the conducting electrons, and so via RKKY. And also you have formation of spin of flux noise on one end. And then we discuss later that. But the other feature that is very bad is that this spin 1/2 can also break Cooper pairs. And so we believe that they are responsible for some variation of gap fluctuations. And these are also bad because you have formation of traps. So let us discuss the first things. Why spins are bad close to the surface? So it is very clear that when you have transmos that are in squid configuration, in which you have these 2 junctions and then you pierce with a magnetic field in order to control, you have an excess noise that we discuss is 1/f, and it is due to spins. Now, the spins can be, now, what we are discussing, don't forget, is this part, right? Because we are discussing metal oxidation, so we are here, we are on this surface. And so, because of this, we have these spins, and this noise, actually, it is a noise that was characterized since a long time. It was originally discussed in the late 80s in a thesis by Westwood, that was a student of Clark, and somehow were the years of ITC, and even if it was an interesting problem because it was shown that this noise is very peculiar, it doesn't varies with the shape of the squid, it doesn't vary with the substrate, it was somehow universal. People were very interested in ITC, and this noise somehow got forgotten. Until the people started to work in qubit, and then they realized that this noise comes back, and it's the same noise. So these are recent measurements that were done in 2007 in the lab of Martinez. And what you see basically that they were using aluminum squid loop, and they were on sapphire substrate with aluminum junction, and the width of the squid was on a micrometer. They were going to very low temperature, 20 milliK, and basically what they were showing is that there is 1/f flux noise, and the level of the noise was comparable to the level of the noise that was studied by Clark in the 80s. And the same feature of the noise that they were discussed in the old times are reproposed here, so that there is basically a temperature independence of the noise below 500 milliK, that there is an area independence of the flux noise power spectrum, especially there is no substrate dependence. And after Martinez did, of course, there were people that were in Delft who were using a lot of flux qubit. The qubits were very different, with very different inductance, very different dimension, and again, surprisingly, the sort of flux noise that they were seeing was comparable. So there was a lot of interest in this year to study to understand what it was. And there were very nice analyses by the Moller group at Stanford University, in which they were looking at different material. And then they see that there was a paramagnetic signal And basically, they were seeing that basically in all the material, what we have is we have some spins that are 1/2, that, and the concentration of this spin is this, 5 per 10, 17 meter minus 2. So we are not so surprised now that we have these spins, because we saw how the aluminium grows, the oxide of the aluminium grows by having this O2 minus that carry a spin. And actually, at the same time, there was many experiments on flux nodes that came from a McDermott group in Wisconsin. And what he was pointing out somehow is that he was able to see some freezing in this spin, and meaning that it was somehow able to give an hint of what the typical interaction strength of these spins that produce the noise. And he found some freezing at around 50 millik. And at the time, it was well, already 16 years ago, we started to think, okay, because there are these spins very close to the metal, we might have interaction between the spin mediated by this RKKY, as I show you. And then if you take the typical value of this RKKY that you have for the aluminium, you put the feature of the aluminium, basically you come up with an interaction between the spins that is comparable. Okay, so somehow in this old paper that we did, we were quite happy because physically we were understanding that this flux noise could be due by interaction mediated by RKKY. But then there were some other problems that came out. First, in this model, right, we were predicting somehow that if you go to very low frequency, this noise will saturate. And instead, there were very nice data from D-Wave, in which they were really studying going very, very low frequency, the 1/2 noise, and it was keeping going up. So there was something else. But then there was a feature that came out that was really very surprising for all of us, that came from some study from MIT many years later, in 2015. So what they did is, they measured on their flux qubit the 1/2 noise. But then what they did is that they took this flux qubit and they look at the noise, the relaxation noise, at the frequency of the qubit. And basically, so we are at the level of 5 to 10 gigahertz. And basically what they were seeing, so as I told you yesterday, we know that when we look at the relaxation of the qubit, what we are probing is the noise power spectrum of the environment that is at the same frequency of the qubit. And then they looked at this T1, and basically for different kind of qubits. And basically what they saw is that the value of this T1, this gamma 1, basically is very nicely given if you assume that is an extrapolation of this 1/2 noise, and when you look at the amplitude, it is the same amplitude of the 1/2 noise that you have at low frequency. And this was really very surprising, because what it is, these plots, what it is basically that this 1/2 noise that we have due to the spins is not a 1/2 noise that has a natural cutoff, but indeed goes even for 13 order of magnitude, and it's quite astonishing. So, and of course, the problem is how it's possible from these spins that interact as we were thinking, this paramagnetic spin, there is no way that you can go to this, explain the presence of this very high energy. And then it comes, we have the other things that we saw, right? Because you see, what you see is that very close to the aluminium you have this O2 minus, but outside, a little bit in the other layer, you have O2. So with the aluminium you remain with molecular oxygen. And then this changed a lot the game, because you see, this, it means that this flux noise is indeed due to two kind of spins. There are paramagnetic spin, 1/2, but there are also absorbed molecular O2, and these carry a singlet spin. And what is the difference? That when you start to have a molecular O2, basically what you have is another term in the Hamiltonian. That is basically what we know is that the molecular O2 interacts strongly with this axis. And basically the strength of this interaction is really comparable to the high frequency scales that we are looking. So with this molecular oxygen into game, we know that there are also some high scale, energy scale that emerge in our problem. So the first question is the following. It seems that this flux noise is characterized by two characters P, but the molecular oxygen are because there is aluminium. The question is that would be very interesting to answer is, what about tantalum? Because tantalum seems that likes to dissociate, and so doesn't have O2. So the question that would be really crucial to see is that, is it possible that if we build squids made of tantalum, there is no high frequency noise, because we don't have this O2. And this is something open that we think we would like to solve. So this somehow close what the kind of spins that you have at the metal-air interface and how they can relate to the noise. Now I told you that there is another feature, that is that if you have spin 1/2 that is closer to the superconductor, then you have this sort of interaction, and then you might break a Cooper pair. And what we think is that because of this, of course there may be other mechanisms, but one expects that there are superconducting gap fluctuations. And the typical scale of this superconducting gap fluctuation is size 0. And now this means that these superconducting gap fluctuations indeed are sort of traps. And if we have some mechanism in which quasi-particles can come, then they can occupy these traps. And then the question is, can they create, for example, some two-level system, or, for example, just trapped electron in traps that they can be excited and so on? And as we will see, the answer is yes, because unfortunately in our system we have source, unwanted source of quasi-particle. So this somehow, so we are discussing what happened at the metal-air interface. Now let's move a little below and consider the metal substrate surface. The metal substrate surface, so we have the substrate and the metal, and we have the substrate and the metal. Basically, also there are traps, and also the main reason is because there is oxygen. So I want to put your attention to a very recent paper that was done in Chalmers group. And basically what they were studying is transmos, and they were studying transmos with different thickness of aluminum transmos that were built on silicon. So first of all, what they were clearly seeing in all this transmos, that no matter how quick you are, there is always the formation of a silicon oxide layer that is about 0.5 nanometer. But what it is was very interesting is they were doing some studies in which they were looking at the different, with this top seal, they were looking at different elements. And basically, with the different dimensions, with different thickness, they can see, for example, when correctly you go from the substrate to the metal. And what it was shown is that there is oxygen at this interface. And this oxygen peak, basically, it's different in depending on the thickness. So the pictures that they have in mind is the following. What is known is that when you grow aluminium, if the aluminium is thin, you have many boundary grains here. If the aluminium is thicker, you have less. And then what is the conjecture is that you have diffusion of oxygen, and then again, because you have this oxygen, then you have formation of possible traps. So far we are discussing only what happened with oxygen coming into contact. Now we know that there is also water. So what happened with the water? With the water, you have this sort of chemical reaction. So you have your aluminum oxide that was already due because it was the oxygen. Now you put the water. And the water has the effect that likes to grow again the aluminum oxide. But, there is a problem that you have dissociation of water while you grow. And as far as I understood, what happened is that you have a formation close to the metal of AlOH3. And this AlOH3 likes to take the aluminium, growth, aluminium oxide, but also production of hydrogen. And of course, in the surface, we have group OH minus. So the typical, I think that the features that you have to imagine what is going on because of the water, sorry, is this one. So in the surface, you have OH minus. So this aluminium is gray, the oxygen is red, and H, hydrogen, is white. So you have OH minus that indeed comes with 8 different configurations for aluminium. Then you have hydrogen can go into this vacancy that were formed before when we were discussing the formation of this oxide growth. And basically what happened is that there are two things. Either an hydrogen can occupy this vacancy, and then we see that this is not really what is favorable. But otherwise, hydrogen can go interstitial. And again, there are 3 different ways. It can be charged in different ways, so we have different geometry. So this is the sort of picture that you have when what we have to expect in our alumina when there is hydrogen. So now there are, I think, study that we did in the past year in collaboration with the group of Sebastian de Graaf. So first of all, what it was done in this study is that Sebastian built a very nice niobium nitride resonator on sapphire, and they are very high Q, single photon, and because of the geometry that it is, they are very magnetic resilient, up to 500 millitesla. And what he did is that he took this resonator, and the idea was to try to understand a little bit more carefully again what kind of spin species you have. And he has 2 tools that he can use to understand this. Of course, one is just to measure this flickering noise of the resonator that we were discussing last time. And the other is just to measure the loss tangent, basically, so the dielectric loss. And what he does, so he built 2 resonators, and he compared, he helped this measurement with other measurements that are done with electrospin resonance, in which you can see what kind of species it has. And the idea that he has is the following, basically, that he measures always quality factor, and he measures with and without the field, and basically magnetic field, apply magnetic field, and so he can evaluate which is the contribution of the noise due to the spins. And another thing that he does is that he anneals. So this is one experiment. The other experiment, he takes the same resonator, he anneals at 300 degrees, and then measure again to see what happened at this noise, if something changed. And now let's see what he sees. So what is focusing is, for example, the frequency noise. So you have your resonator, the resonator has a frequency, but because of this TLS, this frequency shift, basically we know very well from the theory again, that this noise is due to the fact that you have change in the dielectric constant induced by the TLS. And we know many things about this, the noise, as I told you yesterday, that is a 1/f noise, that is a very special noise that comes with the fact that the intensity of this noise paradoxically increases when you go down with the temperature, because we understand this due to the fact that coherent two-level systems that are in resonance with your resonator basically are affected by other fluctuators that basically cause drift in their frequency. So what he did is he compared the level of the noise in these two experiments. One with the out annealing and then after annealing with 300 degrees. And what he sees very interesting is that this noise decreases. So what does it mean? It means that some of these spins, well, some of these electrons, right, or the fluctuators, because of this thermal annealing, disappears. Then it takes and looks at the loss. So the loss, mean the electric loss, it is due. So basically, we want to calculate the quality factor of this resonator. And what we know, that what is relevant for the quality factor are the noise, that is the interaction of this resonator with the coherent two-level system and the frequency of the resonator. And indeed, and what he sees basically is that there is not much difference in the noise with and without annealing. So he sees actually what we were predicting basically, that if you vary the power of your resonator, the loss has a very weakly dependence, a logarithmic dependence, so meaning that the interaction is important, but the loss itself doesn't vary so much. The reduction is not like striking as the frequency noise, but it is only at 30%. So what happened here? Then he looked at the ESR, and then what he sees basically is that originally, before the annealing, he had, you have to look at this red spectrum. So you see, he has a peak of corresponding to spins with G equal to, and then he sees this hyperfine. Now, there was controversy that this is not, but they are exactly at the frequency that you would expect for the hyperfine of the hydrogen. When you anneal, and you can calculate which are the estimates from the intensity of this quality factor, what is the density? And we find exactly what Moller was finding, where what the measure intensity, density that everyone else finds. So we are at the level of 10, 17. But when it then anneal, what happens is that what he sees is that there is, it cannot anneal everything. There are still G equal to, and there is this background that still is there, that he doesn't go down. But what completely disappeared because of this annealing is these peaks that were at this hyperfine. Then, so this he sees by ESR. Then he looked at the loss, as I was telling you, and what he finds is that the loss decreased very little with an annealing. And what instead it decreased quite a bit is the frequency, the jitter frequency noise. So, what does it mean that? This means that basically when you anneal, what you are eliminating is this hydrogen, and this hydrogen that carries Q1.5, they contribute less as a fluctuators to the 1/f noise, and then accordingly you see that the 1/f noise goes down. But on the other hand, what this tells you is that you, with the annealing, you don't anneal two-level system at around the frequency of your resonator. So it means that there are sort of these two populations, right? There are these sort of incoherent TLS that affect so much the phasing and noise, because, and that these has some hope to be annealed. But there are the usual two-level systems that we are worried at this frequency, they are not affected by this procedure. So this is one feature. Now, when, as we saw, in this picture, there are inside there are these hydrogen, right, that occupy this. And I want to show you that these hydrogen indeed are responsible for this two-level system. But there is there was a study about how this two-level system can be formed because of this hydrogen. So as we saw on the surface, we have many OH. And then what you see is that this OH form an hydrogen like the two-level system like this SiO2. So you can it is a sort of rotors. But there are also hydrogens that goes into this aluminium vacancy. But if you look at the energy formation of these are not stable. So these are more likely not important. What instead they found as a favorable configuration is this H+. So you have interstitial hydrogen here that get attached to this oxygen, right? And then it's H+. And now you have a problem, right? Because, okay, how this results in a two-level system? So usually you have configuration like that because it's interstitial, that this hydrogen loves to be attached to one. So if you look at configuration like this, so that one hydrogen is very close to one oxygen, basically what you expect is a two-way configuration like this. And this is a two-level system that is not a two-level system because that can be excited at low temperature because it has a very huge difference in the energy. So in order to have two-level system that we care from this interstitial hydrogen, what you need somehow is that your hydrogen gets very close to two oxygen, so that basically this double-way configuration becomes something degenerate, and so you can have this easily activated two-level system. So you see, it is not only you need really to look for particularly coincidence configuration. And now comes another big problem. And the big problem is the following, that if they do with DMT studies, this ab initio calculation, and they start to say, simulate and see what is the typical energy scale of these two-level systems that are caused by hydrogen. So you start to look first from this defect that are at the surface, OH minus. They can form two-level system as we have SiO2 defects. They look at the dipole, is the 0.2 values that Jürgens see in the studies that he does. So we are in the correct dipole moment, but the big surprise is that the energy splitting of this two-level system is very high. So it's at the order of 10 to the 3 gigahertz. So there is no way that this one is in resonance with your 4 gigahertz cubic. The only way they claim that they can bring this two-level system to be in resonance is either through some interaction or some strain. So you need to deform your amorphous material so that there is some strains that somehow squeeze your energy. So what I show you is that we know that there are interactions, so we are happy about that, and probably there are also strains. Actually, we know that strains are also important. So for the surface two-level system, like this one, we can see that, okay, this interaction is playing a good role because we know that we have many other spins around, so these are not really isolated. Sebastian showed that there are an effect of these spins, so there is interaction. But then let's come to see what happened for these interstitial hydrogen bonds. And then, because with these hydrogen bonds, what you see is that you need, first of all, to find a configuration. But then once you find the configuration, you have the same problem. That you need to introduce some compression in your system because, you see, again, this typical scale of energy that you have is very high. And so, this comes in a very important point, right? That somehow these two-level systems that we are dealing are two-level systems that are strained. And that's, for example, I think might be an interesting observation, because we know, for example, that two-level systems that are in the junction that Jürgen studies without the flip chip technology are more stable than the ones that are in Google done when there is the flip chip technology. And the idea is that there must be some strains due to the flip chip technology, and that's why, for example, you might have more effect of this two-level system, in the sense that when you have some strain, basically, this two-level system gets into the energy level splitting necessary to interact with your qubit. But all of this is something that we are still investigating. So now, we talked about spins, we talked about two-level system, and now comes another sub-chapter, the quasi-particle. So what happened is that in the last few years, it was discovered that we have a continuous, unpleasant source of quasi-particle that is due to cosmic rays and gamma radiation that are eating our chip. So how is possible? So first of all, there are cosmic rays, but there is, in the labs, there is what is called gamma radiation that is due to building, to defect in the building. And actually, what it was measured here is the typical gamma radiation that you have in the lab in Madison, Wisconsin, and this is in Gran Sasso when you go down. And you see basically that the gamma radiation is there, is similar. So, and actually, this gamma radiation is what we really are more concerned for this qubit, because the cosmic rays contribute less, and effectively, if you go down, you can somehow screen this effect. But this gamma radiation is there. So what happened? When you have a gamma radiation or a cosmic rays that goes into the substrate, I like to call it, is for the chip that you have, is really a sort of Big Bang, because as in Big Bangs, you have two phases, right, in which you have the separation of lights and then the separation of matter. Here it is the same. You have a separation of lights that are phonons, and then matters that are charged. And so basically what happens is that if you have a gamma rays, basically the impact, the average energy that is put into your chip is 100 kiloelectron volt, and this is the rate, 8 millihertz. And if you have a cosmic ray, they are a little bit higher in energy, it's 46 Kelvin electron volt, but the rate is less, it's 0.5 millihertz. And this is a huge amount of energy if you compare what is the energy that we have when we talk about qubit. The splitting of the qubit is of the order of 10 micron electron volt. So what happens is that this energy that goes into the substrate basically forms electron-hole pairs in your substrate. And that depends, crucially, on what is the substrate material that you have. Because the energy that you need in order to break electron-hole pair in the silicon is 3.75 electron volt. For sapphire, it's higher. And then what happens is that these electron-hole pairs recombine very quickly, picosecond order, and emit phonons. But there are always 20% of these that do not recombine. And this 20% basically is that if you do the calculation for silicon, it means that for every strikes of gamma rays that you have, basically in your substrate you have the creation of 2 to 10 to 4 discrete charge that comes. And now comes another typical problem, right? That this, depending on what is the kind of substrate that you have, there is the mobility of this charge and nodes. For example, in silicon, what happens is that the electrons move much faster than the hole. So you have a sort of separation between positive and negative charge. So and then I will show you why this separation is relevant. And of course, these electrons start to propagate until they are trapped. And the typical value of the distance that they go before being trapped in silicon is very high, is very huge, it's 300 micrometers. So you see, even 500 micrometers are being told are estimated that is possible. So we have two problems, right? We have a problem that because of this ray, we have phonons that start to go ballistically everywhere, and we have charge that start to move. Now, when the phonon goes ballistically, of course, the big problem is when it goes and hits the aluminium. If it has an energy enough to break the Cooper pair in the aluminium, then it creates quasi-particle. And of course, what is very bad is when it hits close to the junction, because in this case, what happens is that happily, this quasi-particle tunnel through the junction and then cause relaxation or excitation. It can cause, but relaxation. So, as you will see. So let's start to discuss the contribution of the two phonons first and then charge. So as I told you, you have these high phonons that are produced. So let's see what is how they go down in energy, these phonons, how quickly they go down. So when you have high frequency optical phonons, they, at times less than 1 picosecond, decay, and they go to acoustic phonon that are around 13.4 terahertz in silicon substrate. And and then these, because of an harmonic decay, they go into lower energy phonon. So let's see what happens. So when the phonon propagates around 1 millimeter in the silicon, what they saw in these detectors, basically, what they see is that the energy spectrum of this phonon is Gaussian, and then it's already centered around 1.2 terahertz, so we are around 58K. And then let's see how the phonon, because of this anharmonic decay in the substrate, what is the time in which it goes down. So basically you see that it goes like this, scaling, and this is what it means, that basically a phonon, after a few centimeters, has an energy of around 12 Kelvin. So 12 Kelvin, you see, it's more than enough to break the Cooper pair of the aluminium. And after the meters, it is just because of this anharmonic decay at the level of 4K, so it still can break. So there is no way. All the phonons that you get that go ballistically, they can really cause a quasi-particle. And that, indeed, sadly, it is what we observed when people in Google started to look for correlated errors, possibility of correlated errors in the chip. So you know that for quantum error correction, for the surface, error correction scheme of Kitaev, what is really the dead of all error correction scheme is to have correlated errors, because correlated errors are the ones that cause very easily non-detectable errors, so your error correction, you will never error correct anything. So what this is an experiment that were done in the old Sycamore chip, and there were 72 qubits, and Matt McEwen basically studied only 26 of these qubits, and the distance of each this qubit is around 1 millimeter. And the kind of experiment that he did is the following, right? So first of all, he has this qubit, and he set the qubit in the high state, in the state 1. So, of course, there must be probability for this qubit to decay. So basically, if you observe this qubit, some remain, some decay. So when you measure at a small interval this qubit, basically you will find that the majority will stay 1, some unfortunately will decay, so you will expect a standard statistic. And then what he shows is that when the cosmic rays arrived, the gamma ray, he saw that in the chip there was something tragic that was happening. Basically, that all the qubits from the state 1 became 0. So they were all relaxed. And so, for example, you can see here visibly what happened. So you can here see even what is the location, right, of your gamma rays, basically, of your particles, because you see immediately, first they were all blacks, and then the cosmic rays arrive, and basically they all become rotten. And this was something very dramatic. And what for us was really surprising is that when you look carefully, what is the time in which you have this spreading of all this error? This was not little. It was around 100 microseconds. So there was two questions that we need to understand. The spreading, well, that we understand, right? Because as I told you, this phonon, every phonon that comes and it close to the junction has enough energy to break. But why? Why there is this sort of retardation, right? Before you have 5, then you have the striking, and then there is some time. So there is a first point, right? What happened? Why the qubit relax? The qubit relax because when you have the cosmic rays or the gamma rays that arrive, it breaks, creates quasi-particle close, and then this quasi-particle basically tunnels through the junction. And so this quasi-particle absorb energy by your qubit and tunnel and cause relaxation. And this is the typical formula that you have. What important is the relaxation and how it depends. It depends on the quasi-particle density that you have near the junction. But there is a nice feature, an interesting feature that Matt observed, and it's basically that after the cosmic ray, you see always decay. What does it mean then? That the quasi-particles that arrive here do not have a high energy, because what they want, they are cold. Because what they do, they always absorb energy from the qubit. They cause gamma 1. They never cause excitation of this qubit. So it means that somehow they arrive and they are cool. And when we saw that, we saw this is the end for error correction. We need really to solve this problem. So there is the other problem, is this raising, right? And then we started to realize that maybe there is this retarded effect because of this, how the chip is built. So the Google chip is a flip chip. Almost everyone uses this. And what they do is that we have a control chip, we have the qubit chip, and basically all the two chips are kept together by this called indium bumps. So we have indium here. And if you see the volume of the indium is really a lot. So what happened? So we started to see that you have a lot of indium. Indium has a delta of 12 Kelvin. So basically, it is reasonable to think that what happened is that the majority of these phonons goes into the indium, right? Captured by indium. And then in the indium, what happened is that because of this, you have a breaking of Cooper pair, and then a combination of Cooper pair. And then when the Cooper pair recombine, they go and release a phonon of 12K that can go again and break aluminium. And so what it was crucial is to give an estimate of what is the typical time of the recombination that you would expect in the indium bumps. And we saw by using theory, basically, that the estimate is comparable with this. So what happened in this, with this chip is the following, right? That you have your indium bumps, you have the aluminium, the cosmic rays arrive, it starts to put out this charge and phonon. Phonon goes very quickly, the heat, and goes into the indium. And when they are the indium is a sort of absorber, right? Absorb something and then it releases. And that is why we think you have this retardation effect. So how can we correct this correlated error? The solution came by gap engineering. And this was a solution actually that was done, I think, more than 15 years ago by Gershenson initially also. Well, there were studies beginning with SET, in which they were seeing that if you have gap engineering, you can control quasi-particle poisoning. Then Gershenson did it applied to qubit. So we knew that if you want to control the poisoning of quasi-particle, there is a strategy that is very good, and that is to create some gap variation. So let's see what Google, my colleague, did very recently. It was Matt and co-workers. So basically, what they tried to do was to give some shape of the gap profile close to the junction. So basically, you have to build your junction by varying the thickness of the aluminium in the two leads. Because it is very well known that if you decrease the thickness, the delta of the aluminium increases. So basically, if you can grow a thin layer of 15 nanometer, basically your delta becomes of the order of 12 Kelvin. So what they did, they tried they built the transmos. So you see this is the pad. They were built on silicon with aluminium, and they built two kinds of transmos. So there are what they are called weakly gap engineered qubit, and the green one that are strongly gap engineered qubit. What is the difference? In the weakly gap engineered qubit, they built one thick layer of 100 nanometers, so we expect this to Kelvin, but then the weakly engineered, the other thin layer was only 30 nanometers. So what we expect is basically a delta of 5 Kelvin. So you have a profile like this, that is 2 Kelvin, 4 Kelvin, but the qubit that we have is around 6 and 8 gigahertz. So basically the qubit energy is higher than this profile. It means that if you have a quasi-particle that arrives here, it can absorb energy from the qubit, and this qubit energy is enough to make it tunnel through. On the other hand, they built also strongly gap engineered qubit, and what they did is they decrease the layer down to 15 nanometer, so that you have a gap that is 12 Kelvin, so that the energy of the qubit is not enough if the quasi-particle comes cold, and we saw that they are cold, is not enough to cause the passage through the junction, and so the relaxation rate. And then they repeat exactly the experiment that they did the first time. So they set up all of these in the one state, they measure very quickly to see what is going on and to evaluate when they have the striking of the gamma rays to see what happened. And now let's see what happened. So you see initially you have this statistic, right, that you might have some decay of this qubit. But then you see that when you have the gamma rays, the impact of this high energy, basically only the qubit that are weakly gap engineered get the decoherence. The others that are strongly gap engineered remain black. So they are not at all relaxed. And so this was great news because we understand that with this gap engineer, we can correct this correlated error. So this was a very nice experiment. But now comes the big question that was raised by Martinez, that this experiment works well from theoretical point of view, because, okay, we might understand that close to the junction, the quasi-particles are cold, so it's clear that they don't get enough energy to be excited and then tunnel. But, and that was the main question, suppose that you have a high energy quasi-particle that is created somewhere in the paddle. So the crucial question is, this has very high energy, it's very hot. How fast does it diffuse? And can it become close to the junction? Because if it becomes close to the junction, right, and they still have this high energy, then it can pass through. So Martinez, what was saying is that it looks too good, it's not possible, because when if you take that this aluminium is clean, then you see that the diffusion distance of this hot quasi-particle is very big. And indeed, John, in his paper, in which he was saving superconducting quantum processor from decay and correlated generated by Gardner and cosmic rays, right? He did some estimate of what is the typical distance that a quasi-particle goes. So suppose that you have this energy that we saw, that is around 15 gigahertz, right? Suppose that you have this quasi-particle. He took Kaplan, and basically he saw that the typical type of the relaxation is of this order. This is the rate of relaxation, that is 1 over 4.5 microseconds. And so if you take this type of Kaplan, and you estimate what is the typical diffusion coefficient that you have in your aluminium, Let's assume that the main free part of the aluminium part that we have is the thickness of this aluminium, that is 100 nanometer. So basically L is 100 nanometer. Let's take what is the Fermi velocity of this aluminium. What you get is an estimate, and then you put to see what is the typical distance that you have. Basically, what you find out is that basically the quasi-particle, before going down in energy, travels for 449 micrometer. So it is right that there should be some hot quasi-particle that could reach easily the junction and cause a QB decay. So the big question was, we don't see that. So why? So that poses the accent on the problem that it seems that we don't understand yet well what is the quasi-particle scattering physics in this aluminium part. And we tried to do some work on this time estimate, and as I will show you, I think that still there is room to do calculation, because we don't, if you do some estimate based on the theory that we have nowadays, this is not sufficient. So the problem that we need to solve is to see how fast the quasi-particle will relax. Of course, the first question that comes is that the estimate of Kaplan were done with clean metal. Is clean our metal? Well, and if not, how dirty is this metal? The other thing is that we are interested in energy that are around 12 K, right? Because it's 0.5 Kelvin. And so we are interested in energy, in superconductivity that is much below the delta. And then the importance, what we see, basically what I want to show you is that it seems to us that this thing is crucial, because this estimate should be able to guide us to think how to engineer a substrate that doesn't let the phonon reach the qubit. So what I just did very naively, I know that quasi-particle lifetime has two contributions, right? There is a contribution of the combination time that is negligible. Then there is the relaxation time. And for our problems, what we are interested, because the system is at a very low temperature, is we are interested in process in which the phonon goes out, so the quasi-particle relax and not absorb. And we know that if you have a 3D phonon density of states, basically the relaxation time obeys this rule. So it is square over omega dE. So it's E cube. So what we are interested in is to calculate better what is the relaxation time. Is it really true what the estimate that Kaplan made, or is it shorter? Is it faster then? So what an important question is to see what kind of what is the typical value of the wave vector of the thermal phonon that we are interested. And what you see best, because the relation between this wave vector with the electron free path tells you how disordered and how dirty you should consider your metal. So if you take our aluminium films, basically you would expect the wave vector is around 0.5 K, is about 0.5 K, it's 10 minus 2 nanometer, minus 1. And so basically we estimate L to be 100 nanometer, not very precisely, because it seems that they forgot to measure the resistance square at low temperature. So we don't know exactly what is L of our film. But assuming that it is comparable to D, then you see that it happens that we are in a sort of crossover regime, where the product of QTL is more or less equal to 1. So in our film, we are not in the dirty metal limit often. So let's try to see what is the theory that we have for relaxation in the clean metal. So in the clean metal, what I found is the theory of Reiser. And basically, basically what he showed in his calculation. First of all, he considered the situation in which he has a sort of high temperature, in which we have both absorption and emission of phonons. So we are not interested in this because we are a very small temperature. But what he does is that he shows that in the clean limit, the relaxation of the quasi-particle has a huge contribution from transversal phonons. And what he sees is basically that there should be a temperature dependence of this relaxation time that goes with T cube. So basically, if you take aluminium, what you would expect from this theory is to have a relaxation time of the order of 4.7, 10 to minus 8. And so they are surely shorter than what the estimate of Kaplan. So this was, so we have T cube for clean. Now let's see what happened in the dirty limit. In the dirty limit, I found many papers. I think some of them are wrong. I hope I found this paper that seems to be correct. So there is again a riser. And basically what it is important here is that you might have effect of the boundary, you might have effect of this phonon drag as they call, but what I looked and I see is that this phonon drag contribution usually is not very big. So I assume that there is complete phonon drags. And what I see is that if, in the case of dirty limit, what I would expect, according to this theory, is that there is a T4 dependence of the temperature. And if you put, right, and there is some consistencies in these two estimates, because when I go at the crossover, basically, I find the same value of the relaxation time that I would have in the clean limit. So, but then I trust theory, but I wanted to look also what is going on from an experimental point of view. And then I started to look what happened, what is the typical relaxation time that the experimentalists did. And then I found out that when they consider very thin films that are very disordered, only Gershenson found a T4 temperature dependent as one would expect. All the others basically found the temperature dependence that is of the clean, even if with the T cube, even if the film there is no dust, it's really very disordered. And actually there was an estimate from the 20 nanometer aluminium film that was done by Gordon. And basically what I see is that this value doesn't agree with the theoretical value that Reiser found, because he found actually that is bigger. So the first question that comes to the mind is, so it seems that this is something not yet solved. Why, for thin film, disordered films, we don't have T4, but we have T cube? And why Gershenson found T4? So what, I think that we could answer, and the answer was that Reiser himself said, okay, if the phonon in the dirty limit is a 2D instead of 3D, then I expect to have a T cube dependence, and for the dirty film. But unfortunately, the value of this dependence, or the value that he finds, are not in agreement with what we find, and that is the first problem. Because if you try to use this theory adapted to the superconductor, and assuming that he said that in the superconductor, right, you can neglect transversal contribution of phonon. We have the doubts that within superconductor you have to include that, so this calculation was not done. But so we know that if you decrease the dimension of the phonons that you expect, you find the T cube. And why do you expect that? Naively, what I would say is that what happens is that you have your superconductor, you have your interface, the substrate, for example, the interface, different material. And what happens is that depending on what is the velocity of the sound in these different materials, you might have reflection or transmission of this phonon. And in the case in which you have a different acoustic mismatch, you might have reflection, then effectively in this two thin film, basically you have a majority of 2D. And that's what I did. I looked basically at different experiments and see what is the acoustic impedance that I have in the different substrate and in different metals that I use. And the experiment that Gershenson did were hafnium resonate of the qubit on sapphire. And then if you go to see what is the acoustic impedance of the sapphire and the hafnium, basically you see that they agree perfectly. And then what happened basically is that when you have some phonon here, this phonon basically pass through, it doesn't reflect. So basically it is reasonable to assume that when you have hafnium and sapphire, you have 3D phonon, and so you should find a T4 like Gershenson observed indeed. But then the crucial question is, then it is really crucial to understand for different acoustic mismatch what is the dependence, what is the typical relaxation rate that you will find. So an open question that is very crucial to us is to see, depending on the boundary, and the acoustic mismatch, what is the typical phonon bus, what is the dimension of the phonon bus that you would expect. Because of course then you can play with different materials and you can try to engineer in a different way substrate. And the goal here, what will be? Will be to engineer a substrate that reflect completely the phonons before they come, but also that is such that the phonons inside the metal are reflected, so it becomes 2D, and so the relaxation of this quasi-particle is very short. So, very quickly, we produce some calculation on the superconducting limit. And for the 3D phonon case, I find exactly the estimate that Kaplan did for the 3 limit and that Martinez did. So basically, if you have a hot quasi-particle, the hot quasi-particle should travel a lot. So if we have this hot quasi-particle, there is no way that Me's experiment doesn't see any decay. It should see that. It means that the relaxation time is faster. And in my calculation, by using the formula that Reisinger finds, I can push this for 2D phonons, but I still find 100 micrometer, and 100 micrometer is still big. So we think that there is some work that one needs to do, because we think that at least the experiment shows us that in this thin film, the relaxation is much faster. So that concludes the phonon part. What is the open question that we have from the phonon part? Now I left you that we have also the matter, right? That we have the charge. So charge, you see, are created depending on the substrate. They start to migrate. There is a differentiation between electron and hole in the velocity. And we think that this fact that you have this separation between electron and hole is crucial to understand another important feature that was discovered in the last year. Namely, that the charge noise in transmon is very different from the charge noise in SET. And this was somehow very surprising, because when we were talking to Martinez, for example, he said, oh no, charge noise in transmon should be the same, 1/f of the SET, because the mechanism is the same, you have this dipole and so on. Instead, what it is found is that the charge noise in transmons, and these are it could be measured because transmons can be built with some configuration of VJC so that it becomes sensitive to the charge. Basically, what it observed is that the charge noise in transmon is always 1/f squared, and it is bigger. So in this plot, what is shown is the typical 1/f noise, charge noise that you have in SET. And then this is the typical noise, charge noise, that was measured in the transmon. Notice that this noise was measured in different groups, and by group of Decoherence, by group of by McDermott himself, and it seems that they all agree that it is go to f squared behavior, and the intensity is of the order of 3, 10 to -4, compared to the typical 10 to the -6 amplitude of the noise that you have with the charge. how we understood this F square is because of this separation. Because effectively, you have some formation of some current, and then if you assume that you have this charge separation, basically what you see is that naturally you would expect a charge noise that is omega squared. So that goes like F squared. So we understand that the charge migration plays a role for the charge noise. But now we have also started to fill all the gaps in the picture, right? Because I told you, because of this spin, we have formation of trap. And then we know that this electron goes, and they go very far. So they can be trapped in this. And once they are trapped, the question is, can they form two-level system, or are they just trapped quasi-particle? We saw that we could solve this problem with the gap engineering, although this problem highlights the fact that we don't understand at all very well what is the relaxation in thin aluminum. But then, what is bad, really bad, is that because of this electron modify the electric field, and then basically they cause the instability of the other two elements. So, as a result of this migration of charge, what you have is that the two-level system, coherent two-level system that interact with your qubit start to shift. And this is really a huge problem, because with our device, what you do is that it can be a huge problem both for the fixed transmos, right? But also for our device, in which you basically can tune, because you cannot afford every time to tune again your system. So we need really, and this is, I think, the most demanding, the most crucial problem that we have now, that we need to solve this unpredictability. So what we show is that indeed, if quasi-particle goes and occupies some of these traps that are induced by gap variation, there can be a formation of two-level system. This two-level system we started to call QTLS because they are related to this quasi-particle. And the first time that we came close to this QTLS and that we realized that there were 2LS that were different from atomic 2LS was by looking again at experimenting resonator with Sebastian. So, now I'll show you. Basically, what he did is he always studied the loss in resonator. He can study loss and he can study the frequency noise, right? But actually, if you study the loss, from the loss also, you can see when you have a two-level system. Because basically, if you study the quality factor of the resonator, sometimes you might see that the quality factor become very bad. And that becoming very bad means that there is an interaction with a two-level system. So even by studying the quality factor, you can resolve a two-level system. And this is what Sebastian did. And in this study, what he did is that he increased the temperature to 300 milliK, and then he decreased again the temperature. And then he found something that we found really very weird. Namely that for a low temperature, you can see a two-level system that is stable. He increased the temperature, and this two-level system gets shifted completely, and then it goes back. So it means that these two-level systems are such that their energy, activation energy, is not the order of Kelvin, like you assume from atomic two-level system, but they are indeed activated around 300 milliK. And so we started to see what is the typical variation that we would expect for niobium nitride. And then if you assume that you have some percentage of fluctuations in the niobium nitride, basically you see that the typical fluctuations are around 200 milliK. So it is reasonable somehow to expect that this QTLS could be originated by this fluctuation. There is another important point that he saw, that when he sees this very weird 2LS and he follows them, basically see that they are extremely coherent. So basically see the coherence of the resonator, they are very coherent. And the other things that he saw that tells you that they are different from others is basically he could vary them, he could inject current in this resonator, and namely vary the delta of the resonator And basically what he could clearly see, and that was a smoking gun, was that basically because of the variation of the delta, when he studied coherent 2LS, the special 2LS, also it varies as when it follows the variation of the delta induced by the magnetic field. So this is really a strong indication that these two-level systems are special and they react to. There is another point, I don't know, I didn't put here the picture, but it was crucial, and I will tell you, is the fact that for this two-level system, you see, you expect a typical, that they are not uniform distributed, right? Like, for example, we know that in the physics of glass, we expect two-level system at all frequency. Here, instead, what you expect if the two-level system is originated by this gap variation, that it has a typical energy, because if this quasi-particle occupy traps that are very shallow, there is very easily these traps can be excited, right, and then this quasi-particle can annihilate. So this is something that we don't expect. And then if, for example, these gap fluctuations are very big, also they are very unlikely because the probability to find this trap basically scales exponentially with the size of the depth. So, and typically actually, what Sebastian saw is exactly this. That if you look at what is the distribution in energy of this QTLS, you see that for high frequency there are no QTLS, for low frequency there are no QTLS, but for a typical, for example, for this nitron was around 5-6 gigahertz, then you see that you have this 2LS. So what is this effect of Q2LS? Of course, they can be coherent 2LS and interact with the qubit, but I think that what it is special about these electrons that can be trapped is that somehow they form an additional bus apart from phonon to the lax of usual 2LS, because what happens is that this electron quasi-particle here, for example, in this configuration, can easily get some energy for conventional two-level systems, so this gets relaxed, and these get escape, and then can be recombined and so on. So I think that from Jürgen analysis, we saw that the two-level system, if you look at the typical time of relaxation of the two-level system, and you assume that is only phonon, this is not sufficient. There must be some additional mechanism, quasi-particle. Okay, this is another possible, okay, due also to quasi-particle, right? There is another mechanism that we think can be used. And also, you see, this also is a mechanism that can create both relaxation, but also shift to a level system. Now, the crucial question is this. Do we have quasi-particle? And last year, there was a nice workshop organized in Lesuch from the community of very disordered superconductor. And basically, after this workshop, Benjamin Sassepé produced a plot. And this plot is that you have the kinetic inductance and then you have the quality factor. What people are very interested is to find some material that can be here, so that you have both a quality factor and then inductance. And he looked at different material, different resonators that were built from different groups, and the resonators were always around 5-6 gigahertz. And basically what he found is that there is a relation that all these measurements follow this sort of line. And if you do, we call it the BS law, and Michel immediately said these laws need to be falsified. And but if you basically look from this law, basically what we estimate is that for all this material, there is always a quasi-particle for this volume. So basically, we know that there is always some non-equilibrium quasi-particle. An interesting piece of news was done a few months ago when I was in Aspen, because from Microsoft, they show indeed that they were able to prove their qubit indeed are violating the BS law. And the reason why they have less quasi-particle than all the other. And the reason why they have less quasi-particle is because they somehow build their qubit with some special traps that didn't want to tell us. But so it means really that we really need, there is possibility to violate the BS law, but what you need to do, you have to work. You have to really engineer some traps, because the quasi-particle, you see, there are always some residual quasi-particle. So we are slowly coming to the conclusion, a lot of information, right? But I think that one of the main things is that this standard tunneling model does not apply to our decoherence, right? We understood why. Because we are dealing with surfaces that have spins, that are fluctuator, incoherent fluctuators, and this affects greatly, and I think we proved nicely with this experiment in resonator, they affect how the phasing and the relaxation, how the phasing, sorry, of the TLS are affected. But from this theory of the interaction with the fluctuators, you don't see effect in the gamma 1 of this qubit, right? Because the kind of relaxation that you expect from a buffer fluctuator is basically irrelevant. And so you would expect that there is, the relaxation is always due to Faoro. But then, unfortunately, if you do the naive calculation, you see that, and we know the Faoro play a role, right? Because as you can show, there are these nice results of the Caltech group in which, when they do this engineer membrane, they somehow are able to improve the gamma 1 of the qubit. But then I think that there are, but then what I want to say is that the suspicions that we have is that indeed these phonons that we are dealing are not 3D again. Maybe they are 2D. And so in this case, the relaxation is increased because we are dealing with the 2D path. The reason why they are not 3D for sure is because if, for example, you just think that they are, that your two-level system are relaxed by phono, there is no way. You expect that the relaxation rate of the TLS due to phono scale like the level splitting cube. And if you took a measurement of two-level system at 5 or 1.2 gigahertz, you clearly see that this law is not observed. Although, so one can think, okay, maybe we have additional relaxation mechanisms due to quasi-particle, but we need to prove better this. Or maybe the key point is that we need to understand a little bit better what is our phonon bus around, because we have also a problem with quasi-particle relaxation. There is also one thing that is very important, I think, to answer, is that you have indication from Alibaba and from your pop that if you look at two-level systems that are at very low frequency, it seems that the relaxation time is very big, in 50 milliseconds. Although, even here, there is a problem, because the kind of experiment that you unpop basically is always pumping. And so there is a possibility that he is doing something similar to MIT, that basically is pumping continuously, and what happens is that he is evacuating quasi-particle. And so, indeed, it's not really this is not really the fact that the relaxation is long into a level system, but it's the quasi-particle are getting out of the system. So this is, for me, an open question, and this is actually a very important question, experimentally to solve. We need to look at very low frequency and do a nice experiment like Jürgen did, in which you basically write in the two-level system, and then you can really study what is T1 and T2, because it will be a very important information to see, to understand if this two-level system at low frequency indeed have a different path, they have longer time, and maybe they are more coherent. Because you see, there is an indication that if you go to low frequency, there are people that want to go to low frequency to build a qubit. Maybe it's true, you have less two-level system, but then the crucial question is, these two-level systems are really very coherent, because if they are very coherent, I'm not sure it's a good thing, because it means that once you swap information into this two-level system, it is really lost forever, because this system is coherent. So we need really to, there is an open big question that we need really to solve. So I hope that I told you, and I hope to highlight also the things from a theoretical point of view that we need to solve. We need to understand better what is the phonon bus that is a two-level system C. We need to try to understand better what is the relaxation and how these estimates are affected by the acoustic impedance of the border. Because this is important information to engineer. Because if we don't solve the stability of this two-level system, then we are in a big trouble. But I think that there are some indications of things that we can look at. And there are indications from this experiment of what are the problems that we don't understand. Okay, I finish here.
So I remember this is the last lecture of Faoro. So it is your last chance to ask questions. Okay, so thank you.
Question.
Yes.
You mentioned, if I got it correctly, you mentioned that there are some data which are beyond this limit which Benjamin was discussing.
Yes. Yeah, they show us, they gave us a number of their quasi-particle density that is much less. We asked immediately what is the reason. They have traps, but they didn't say.
But you mean there is a data on this plot relating kinetic inductance and quality vector.
Yes, that goes.
Which goes beyond. And also there is some information about the number of... No, just the point.
The point.
The point.
Yes. So, and of course the question that immediately we were asking is, you have trap? And they say yes, but I will not tell you what kind of trap. So probably, yeah. The idea is that probably they build some special substrate that is, right, your, but we don't know. But you have to work. I mean, you have to do it something, to engineer something in order to violate this law. Yes?
But your this last statement basically assumes that this law itself originates purely from quasi-particles, right?
What do you mean? Yes.
Yes.
Because
but we don't have any kind of general theory about this broad range of parameters, right?
Not really. But,
Well,
I think, yes, were very naive calculation, right, that you did, but...
So that's all, I guess.
Yes.
Thank you for the lecturer for his lecture.